Okay, the last thing that I want to cover is called the frequency response plot. And the frequency response plot is intuitively very simple. It's just a plot of omega along the horizontal axis, or frequency, and either the magnitude of h of omega or the angle of h of omega along the vertical line. So the most common one would be plotting omega versus, well, I'm going to list what the entire h of omega is, and then we can plot whatever we want. So I'm going to, since h of omega is a complex number, I'm going to plot it as if it was I'm going to find its, since h of omega is a complex number, I'm going to find it as a complex number, and then we can choose which portion of it we want to plot. For this particular transfer function, h of omega is equal to 1,000 over j omega plus 1,000. And we already found what it was for omega equals 1. For omega equals 1, it was, just before we write this down, I want to take a quick mathematical aside here, like we sometimes do, and review how to figure out magnitudes and angles. If you want to find the magnitude of this number, AB over CD, it's equal to the magnitude of the numerator over the magnitude of the denominator, which is equal to the magnitude of every single component separately. Next, to find the angle of AB over CD, it's equal to the angle of the numerator minus the angle of the denominator, and that's equal to the angle of A plus the angle of B. So in other words, multiplying complex numbers, you add their angles, minus the angle of C plus the angle of D. Okay, so we've already found out what h of omega is when omega is close to 1 or very small. And we found it's equal to approximately 1. And again, that's because this is exactly this number. And so the angle, let's start off with the magnitude of this. Is going to be the magnitude of the numerator, which is the magnitude of a real number is a real number, divided by the magnitude of j plus 1,000. And we found that that's almost exactly equal to 1,000 when there's a big difference between the real part and the imaginary part, and that's just 1. So this would be 1, and 1 has an angle of 0 degrees. Okay, so for 10, we'd have 1,000 over j10 plus 1,000. And again, you could get a pretty good approximation. We could say the bottom here, the denominator, is pretty close to just 1,000. So this is 1,000 over 1,000, which is pretty much just 1 at an angle of 0. If you plugged it into your calculators, you would find it's exactly this. So it's still incredibly close to our approximation. Now for 100, we get something that's, again, our rough calculation is that this is still difference by about an order of magnitude, by about a factor of 10. So if we were to calculate it by hand, we'd still end up with the same result. We'd still end up with 1. If you put it into a calculator, you'll get exactly 0.995 at an angle of negative 5.7 rather degrees. Once we get any larger, at 1,000, our shortcut for saying ignore the smaller real or imaginary part if there's a difference of a factor of 10 or more breaks down. We can't do that. Now we have to plug it into the calculator. But once we get higher values, you can see the pattern on the left. I'll just simply write out the results. Once again, rather I will write it out, because now we can do the simplification again. We can say 1,000 over, we can say 1,000 over J 10,000 plus 1,000 is going to be pretty close to 1,000 over J 10,000. And so that's going to be equal to, that should be 10,000. So that's going to be equal to minus J, since remember 1 over J is equal to minus J from last year. So that's going to be about minus J over 10, or 1/10 at an angle of, let's see, what angle is minus J? If we were to graph that with a real part and an imaginary part, and we've got this 1/10 and it's purely imaginary, that would be at a minus 90-degree angle. So that'd be minus 90 degrees. So there it is, 0.1 at an angle of minus 90 degrees. We can continue doing this for larger values. The same reasoning holds true now. It's dominated, this is going to be dominated by the imaginary part. And now we're going to get 0.01 at an angle of minus 90 degrees. We still haven't talked about what the frequency response plot is after all this, but that's just the plot of this table. And so the magnitude, frequency, response plot is the magnitude of h of omega. And so it starts off at 1, and it, if you were to plot it, it goes down like this. And we say its cutoff point is at 1,000, where its magnitude is 0.707. This turns out to be exactly 1 over the square root of 2 at an angle of negative 45 degrees. And the reason for such an unusual looking place where we define when the filter has cut things down from 1 to 0.707 as being the cutoff frequency rather than something that seems more obvious, like, for instance, 0.5, is that if you've got a filter and it cuts down the voltage by 0.707, by 1 over the square root of 2, then if the result's going through a resistor, it'll also cut down the current by 1 over the square root of 2. And that means it will cut down the power by 1/2. So this is also called the 1/2 power point. I've only seen it called that in a textbook. It's, no engineer would ever call it the 1/2 power point. They'd call it -3 dB point for reasons we'll talk about in a couple of classes. And this is our magnitude plot. So just the magnitude of our filter. And similarly, you can also have a phase frequency response plot. And although I'm drawing everything in terms of omega, you'll also see them in terms of frequency, Hertz type frequency. And you can see that this begins at 0. And then it goes down and ends up at -90. And at -45, that corresponds to 1,000, which is our cutoff frequency for both. And that's how to calculate the frequency response plot given a circuit.